Hello and welcome back. So far, we have a decent amount of understanding on PCA. With visual understanding, you would have got better clarity. But let us try to understand how mathematically it does. How principal component analysis mathematically doing the things internally. So the main goal of principal component analysis is to extract the variance between features, right? To extract variance between features, first we need to calculate the covariance matrix. Feature and feature, the relationship matrix we need to find. If you pass that matrix to eigenvector decomposition, eigenvalue decomposition, that will decompose the matrix into eigenvectors and eigenvalues. The eigenvectors are the principal components. Eigenvalues are the essence how much each principal component extracted from the data. Eigenvalues and eigenvectors are pairs, right? The eigenvector 1 and the lambda 1 are pair. Eigenvector 1, how much essence captured, will be quantified by lambda 1. Eigenvector 2, eigenvalue 2, lambda 2 will explain how much essence eigenvector 2 extracted, like that it is, right? So the eigenvectors are the principal components and eigenvalues are the explained variance ratio, we call it as. Explained variance ratio is nothing but the amount of essence the principal component extracted from the data. What is the data here? The covariance matrix. First we need to find the covariance matrix and then pass it to the eigenvalue decomposition. That will find the principal components and the explained variance ratios. And the now when principal component analysis uh, when after applying the eigenvalues, eigenvectors, right, you take the principal components and multiply them with the original data to find out the values, the transformed data. So let us see the math, how it works. So here I have taken the data set with the 5 columns, x1, x2 and so on x5, and there are m number of rows. If you look at this data, the superscript in brackets 1 denotes the row. This is the first row. See, all superscripts are 1, all superscripts are 2, all superscripts are m. That means there are m number of rows. And subscript tells you the column x1, x2 and so on x5. Okay. And the first thing PCA will do is mean centralize the data. It calculates the x1 bar, the mean of the first column, mean of the second column, mean of the third column, like that. It calculates for 5 columns and then subtracts the mean, the first column's mean from first column, second column's mean from second column, like that. It is centralizing, mean centralizing the data. Now it takes the mean centralized data and transforms it, okay, like this. This is the original matrix, and when you transform it, what happens? The columns become rows and the column headers, I actually kept it here, and rows become columns. Okay, our goal is to find covariance matrix and then pass it to the eigenvalue decomposition, which extract the covariance inside the data. You pass covariance matrix, eigenvalues decompose covariance. If you pass co-occurrence matrix, eigenvalues decompose co-occurrence in the data set. That's whatever the type of matrix you pass, that type of essence it will extract. Okay, so the covariance formula is what? Sigma I is equal to sigma k is equal to 1 to m xki minus xi bar xjk minus xi bar, right? So if you look at the next slide, right, you will understand what this formula I'm actually. So I am trying to get in each cell, after multiplying these two matrices, I am trying to get in each cell the covariance between one column and the other column. So what I will do is I will take x transpose and multiply it with x, or xc transpose, centralized data, mean centralized data as transpose, and multiply it with x. So if you multiply x transpose with x, what happens? This row multiplies this column, right? So this is actually x1 minus x1 bar, x1 minus x1 bar, right? This second row value, like that mth row value, and you are multiplying them with. So what are you multiplying? X1 minus x11 bar into x11 minus x11 bar, x12 minus x212 minus x1 bar into x12 minus. So same values mean centralized. The same column is getting element wise multiplication. That means it is going to be the correlation between the column and itself, the x1 column and itself. And if you multiply this row with the second column, you will get the correlation or covariance between the first row, first column and second column. Multiply first row with the third column, you will get the covariance between first feature and the third feature. Feature and column are synonyms, right? In database you call it as column, and in data science you call it as feature. So first feature and third features covariance you will get. First feature and fourth features covariance you will get. So ultimately, after multiplying x transpose x, you will get 5 by 5 matrix. You have 5 features. After applying principal component analysis, you should get 5 principal components. Using those principal components, you are going to transform your original data, right? So when you multiply xc transpose x, you will get a covariance matrix between 5 features and other 5, the same 5 features. Okay, so a 5 by 5 matrix you will get. If you see this matrix, it may look clumsy, but whatever I explained right now, I just tried to put it here. x1 into x1 it is, x1 into x2 it is, x1 into x3, x1 into x4, x1 into x5. So it is the covariance between x1 and x1 itself, covariance between x1 and x2, x1 and x3, x1 and x4, x1 and x5. Like that, each cell will capture the covariance between a feature and the other features. The diagonal values are the feature in itself. This is x1 and x1, this is x2 and x2, x3 and x3, x4 and x4, x5 and x5. The diagonal values are the covariance between the feature and itself. And the upper triangular matrix and lower triangular matrix are same. If you look at the color coding, right, this color and this color, now this cell and this cell are having the covariance between x1 and x2, right? This is x2 and x1 and this is x1 and x2. If you see this yellow and yellow, this is x5 and x2, this is x2 and x5. So the upper triangular and lower triangular matrices are same. So it's a symmetric matrix, a covariance matrix we have got. Okay, so we pass this matrix into eigenvalue decomposition, which will extract the principal components, principal component 1 till principal component 5. These are the eigenvectors of the covariance matrix. This covariance matrix, mean centralized covariance matrix. And when you do mean centralization only, you get covariance, because the covariance formula is what? x1 minus x1 bar into x2 minus x2 bar. So that's what we did here, right? So you get principal components which are nothing but the eigenvectors of the covariance matrix. xc transpose xs passed into the matrix is passed into eigen decomposition, and you have got principal components and the eigenvalues are explained variance ratio. In PCA we call these values as explained variance ratio, right? We normalize them so that we get the total of lambda 1 plus lambda 5 is equal to 1. Okay, leave that point aside, but lambda 1 till lambda 5 are the explained variance ratios. The lambda 1 explains how much PC1 extracted, lambda 2 explains how much PC2 extracted, lambda 3 explains how much PC3 extracted. So these values are going to be, the lambda 1 is going to be higher, it's going to be little less, it's going to be little less, it's going to be little less, and it's going to be even less. Why? Because the first principal component is going to go in a direction where the data is strongly correlated, right? That's going to extract the more essence. Okay, the second one it will little less, third one even more less, like that it is. Okay, so we have passed the mean centralized covariance matrix, or the x transpose x matrix, and to the eigen decomposition, and we found principal components and the vectors, the principal, the eigen values, which are explained variance ratios. Now what you need to do is, you have a data set of size m by n, m rows and n columns. Here the 5 columns, m by 5, you have a data set. After applying PCA, you should get a m by 2 or m by 3 or m by 4 or m by 5, right? Your rows should not get distracted, your columns should reduce. To do that, what we'll do is, If you want to reduce your data set to size 3, the column, the dimensionality 3, the number of columns 3, then you take first 3 principal components, because these 3 principal components will extract more. Suppose that the first principal component extracted 50% of the essence or explained variance ratio. Second one maybe 10%. Third one maybe 5%. Right? Like that, if it extracted, right? If you take these 3 principal components and try to multiply your data set with these, right? 50 plus 10 plus 5, 65% of your total data's essence will be extracted. Let us see how it actually happens. So I have taken 3 principal components. Our original data set is m by 5. I am multiplying that with 5 by 3. I will get a m by 3 data set, right? M by 3 data set. So the matrices, m by n and n by p, multiply, you get m by p, m by 3. So these are the z1, z2, z3, the transformed data, and the data extracted, the covariance extracted data, right? The z1, z2, z3, z1, z2, z3 is the covariance extracted data. So you can use this data to build a model. Okay, so if you have 1 million columns here, if you apply PCA, you can reduce it like that. After finding principal components, you multiply it with your original data and you find the principal component. That's how it works mathematically. So in coming session, we'll see a code example on how to use PCA and reduce the dimensionality and use it in a supervised learning algorithm and see whether our PCA is working or not. Thank you.